So this is part 4, and this mostly concerns alternating current, the idea that current can be travelling in alternate directions. So let's get straight on and define what these things mean. You see, DC current, such as something coming from a battery, will always travel in the same direction. The flow of electrons will always be in one direction and will roughly always be of the same amount, which is why we talk about 6 volts direct current. That's the current flowing in one direction. However, if you've got alternating current, AC, then there's a change in direction. At the top here, at the peak on this side, that it's flowing one way. Whereas at the trough on the other way, it's flowing in the opposite direction. So this wave, which looks just like an ordinary sine wave, is actually telling us that the current is changing direction. And the frequency tells us how often it does this. If it's got a frequency of 50 hertz, it's changing direction 50 times every second. Now, comparing the voltage of the top with the voltage of the bottom is quite difficult. This, for instance, could be 200 volts, whereas this could be 320, and they seem very different. In order to compare them, you have to take what's called the root mean square value, which is written down here. The root mean square value is literally what it says. You square every point, you find the mean, and then you take the square root of that number. If you do this mathematically, you find out that you don't have to do that for every single time. You just simply divide the peak voltage, which I've said here was 320, by the square root of 2, and you get exactly the same result. And that formula is in the log table for working out the root mean square. Now, why do we use the root mean square? Well, we use the root mean square so we can compare DC to AC, particularly in terms of the power. The power in AC is the root mean square voltage times the current, whereas in DC it's simply the voltage times the current. Power, power usage, energy usage, all of these need the root mean square value rather than the peak value. But the two, as you can see, are related fairly simply to each other, and we don't have to do a huge amount to. So here is a more easily graphical representation of the two. You can see the green line at the very top is the peak voltage. You divide by the square root of 2 and you get the root mean square voltage. Here it's written as 0.707. That is the square root of 2, basically, divided 1 over the square root of 2. And as I've said here, it's used to compare the power output, the difference in the power output of the two. Okay, so why even use alternating current? Why not use DC for everything? If you need to change everything that you use back to DC for most devices, apart from the lights, everything we use uses DC and has to be rectified, changed from AC to DC. The reason is transformers. Power station produces maybe 500 to 600 volts. It's then stepped up to 50,000 volts and then transported at those 50,000 volts till it gets to a step down transformer near your house, where it's slowly stepped down, usually in 2 stages, to 240 volts. Now, why bother? Why not just send everything at 240 volts? And the reason can be explained by a certain London brewer called Joule. Mr. Joule came up with his first idea of how energy was related to current very early on. He, you see, understood that while power transmission was in P equals VI, energy lost, Joule's law, was I squared R. This simply means that voltage has nothing to do with the amount of energy you lose, but it has got to do with power transmitted. So if you have a very high voltage and a low current, you'll lose less energy, Joule's law, because the square of the current gives you the power loss. So a current of 1 loses 1 joule for every resistant. A current of 10 loses you 100 times more because it's the square of 10. So obviously, you try to keep the current to the absolute minimum. And this means very, very large voltages, which do absolutely no harm at all. Most people are against pylons because they don't like looking at them. I've got a little bit of sympathy for that, not much, but a little bit. But no sympathy for people who then try and do pseudoscience into the fact that they're all causing cancer, like the 5G network causing the coronavirus. Absolute pants. So high voltage, small current, less energy loss, less harm to the environment. Don't forget that if we lose energy transmitting it from the power station to your house, we have to generate more and ruin the environment more, create more pollution. So if we use high voltages, we have less pollution. That means we have a better environment. Here's a little calculation of the suit. You can see here how we do the calculation. You've got 100,000 watts to send, so you send in a 12 ohm cable. Now if you start with 100 amps, you end up losing 120,000 watts, i.e. more than you send. But if you use just 1 amp instead, which means you have to use a much higher voltage, 100,000 volts in this case, then your loss in the form of Joule's law is only 12 watts in exactly the same cable. 10,000 times less. And that's simply because of this square in Joule's law, the idea that it's I squared. So why do we use high voltages? Because to reduce energy losses, and that's due to Joule's law, which is written in the logbook as energy is proportional to I squared. This is the experiment we do to prove Joule's law, and you notice once again we've got exactly the same setup. You have a variable resistor and an ammeter. You can even put in a voltmeter if you want. It's of no use in this. That's meant to be a voltmeter. You can also replace this with a power supply, 6 volts, positive and negative if you wish. Because it doesn't, this one I've left the battery in because it doesn't matter which way around we have the battery. We can also use alternating current actually for this experiment. It works just as well. Basically what you do is you heat up some water with a heating coil at different currents. So you'd start with 1 amp, then you do the same for 2 amps, and you keep the time fixed because there can only, as you know, be 2 variables. An important thing to remember if you're asked a tricky question, sometimes the answer is you can only have 2 variables. Why do we keep the amount of water constant? Why do we keep the time constant? Why do you keep other things constant? Why keep the length of the wire constant when you're measuring tension? All of this is because you can only have 2 variables in an experiment. So we do it for all these different currents up to 5 amps, and we plot a graph, and the graph plot is the change in temperature you get, change, not total, change in temperature, that's quite important, against the square of the current you provided. Now, a recent experiment, they gave you the figures, but they didn't give you the change in temperature, they gave you the final temperature, and you had to calculate the change in temperature. And if you didn't do that, you ended up with a graph that didn't go through the origin, which was a bit of a pity. But if you do that correctly, you've proved Joule's law. A version of Joule's law is here. Power is proportional to I squared, can also be written as change of temperature is proportional to I squared. Proving Joule's law is the point of the experiment, and basically 6 readings of 6 different currents for the same time, for the same amount of water, and you're fine. Now you adjust the current by sliding the slider on the rheostat. We might have mentioned earlier that in an experiment you're expected to state what you change. Not that you change the resistance, but how you change it. You slide the slider on the rheostat. Now, the electroscope. When an electroscope is neutral, all the charges, as you can see, are apportioned, as you can see them here, arranged randomly or paired. As soon as you bring in a charged object, what happens is all of these positives are pushed away, they are repelled. Now this means that the whole stalk and the gold leaf are charged positive. Now because they're the same charge, they repel each other. So the gold leaf is simply being repelled by the same charge on the stalk. And that's what you see. And this is how you sense the presence of static electricity. Now, fields. What is an electric field? It's basically the region where a charged particle feels an electrostatic force. Just like a magnetic field is the region where a magnet feels a force other than gravity. Field lines are the direction a positive charge, or a north pole if it's a magnetic field, would travel if allowed to travel in this field, where they would tend to go. So a field line describes their journey. An electric field just says that's the region that something can be felt by an electric charge, or a magnetic field by a magnet. So how do we work out these forces and charges? We lose Coulomb's law. Coulomb's law, they're written as a law, which you can put into a sentence, and here written as an equation, which is what's in the book. This, in the yellow, you can see, is the constant of proportionality, the thing which changes it from a proportional sign to an equal sign, the constant. Now, it's written in this bizarre form due to the fact that it's got to do with the surface of a sphere, the outside surface of a sphere, which is the thing which is changing these two, changing the proportionality to the equation. Now, once we have the equation, we can simply do calculations. Here's a simple calculation between two charges. One's at 2 Coulomb, the other's at 4 millicoulombs. Sorry, that's 1 to this, so it's 4 times 10 to the minus 3 coulombs. And we can put these in together with this figure, as remember the permittivity of free space, which is down here. There it is. 4 pi is obviously pi as we'd expect, and d is the distance between the two of them. So we put all the numbers in. There we are. That's the, as you can see, the 4 millicoulombs, 10 to the minus 3. There's E there, and that's the distance squared, the distance being 2 meters. All, as you know, everything should be written in meters. And we get an answer. Now, because it's a force, it's newtons. It's a very small force. These are tiny forces. These are tiny amounts of force. To get a large force using electrostatics, you need an enormous amount of charge. But don't forget that these are all done thousands and millions of times in tiny little spaces. So electrostatic charges move between, are most important when things are not 2 meters apart, but which are 10 to the minus 18 of a meter apart. Then you really get some serious force between two charges. Now, as well as the force, you can also use the force to find what's called the electric field strength. The formula again is in your logbook, and you simply divide by the charge not involved. So if you are 2 meters away from a charge, you use the charge you're on. So this one is the one. So you're talking about the electric field strength in this one because you're dividing by 2. You're talking about the electric field strength here, where the charge is not important. It's just the field coming from that one. That's what you're measuring. The charge coming from the 4 millicoulomb. And this is how it's written down. And it's newtons per coulomb because you've taken newtons and divide by coulombs. And as I say, it's in the logbook. You just divide by the charge. Now, sometimes you can rewrite the other equation if you wish. Q over 4 pi epsilon d squared, where you've taken away one of the q's and write it like that, if you like to remember that. But that's not in the logbook. The other one is, and so that's the one you should get used to using. Okay, so various devices are mentioned on the syllabus. This is due to the Science and Technology in Society, which forms the bones of question 11 and also pops up in question 5 and occasionally in question 12. And in other places, very occasionally in small lumps. Now, one of the things mentioned is this thing called a precipitator. This is where you have very fine wires called corona wires. Yes, I know, ironic. Corona wires here. And they have enormous electric fields around them. Now, smoke comes out of a chimney and blows through these wires. After it's gone through the wires, it's all charged negative. The smoke is all charged negative. And because it's negative, it clings to positive plates, which are placed just after the corona wires. This acts as a scrubber, removing gases, ash, anything from chimneys. So that in Ireland in particular, there's very little coming out of industrial chimneys, almost nothing. Most of the stuff coming out of industrial chimneys, which people constantly have in pictures, is actually water vapour. They're actually clouds. If you see a picture on the news and there's a picture of a chimney behind a reporter and there's billows coming out of it, that's all water vapour. That's all water vapour. There's very little smoke or dirt in that because of these scrubber devices. Now, of course, some of it will get out, and you don't need an awful lot to ruin your day or your life. I don't know what. There must be something you can get from pollution. Someone will think of that. What is it? Someone will shouting it out now. The final section, because it's in here and because we're only at slide 19, I just talk about potential difference. Now, work is the amount of energy it takes something to climb. If you're doing work, work is force times distance. Work is force times distance. Here we have the force, which is related by the Q, and the distance, which is related by the potential difference. So, in the same way as the amount of work you do to lift somebody up to the top of a staircase is their weight times the height of the staircase, the work done electrically is the charge you've moved times by the voltage you've moved it across. So if I have a charge of 7 coulombs and I move it across 100 volts, then I've done 700 joules of work. This is dead convenient. The formula here, which is essentially saying the same thing. And it gives us a definition of what's called potential difference as well. Because we can reverse this idea and say the work done moving a charge, particularly a charge of 1 coulomb. So the work done moving 1 coulomb of charge is also called potential difference. So if the charge here is only 1 coulomb, then whatever you gain by lifting up the staircase is the energy and the potential difference. They are the same number. And because they're the same number, we can say they're equal to each other. Okay, the unit of volt can also be written therefore as joules per coulomb. And you get a definition of the volt as well. And also potential from a point. Potential difference is between 2 points. Potential is at any point going all the way back to Earth. So going literally back to the planet where the potential is 0. So the difference between the planet and any point, that's called its potential. And the potential difference is between 2 points which are not the Earth. Okay, so you've got 2 questions therefore to do. This is a nice long question which involves everything. You can choose to tackle this one. The last section is a little bit interesting. You can think what would happen with a coil. With a coil, remember, as well as the resistance, you also get something called back EMF. Now, think how that would affect if you've got an extra back EMF. And the diode, remember, that's the ultimate pop band. Yes, one direction. Only allows in one direction, okay? Which means you can only listen to shit music. Okay, finally this one, which I think is possibly the better question. It's a bit of everything on this one. Forcing you to look up what things are. Asking you what F is the core, or in fact the whole thing of a transformer. And the great thing is, that's in the logbook. You only have to look it up. As is that. And all you have to say is what they are by looking up the symbols in the back of the logbook. This was not rocket science. Describe the function of G. Well, it's a diode. What does the diode do? Sketch an input and output. Well, you've got if this is a smoothing device, it's a transformer. So you're looking at, AC going to DC. Then it says, photograph a device, calculate the maximum energy. Well, there's the fault on the outside. You've got the voltage and you've got the capacitance. With voltage and capacitance, you can find energy stored, can't you? Equals half CV squared. And then you've got a little bit about Joule's law. So I think this is possibly the one I'll be putting up, but I'll give you the choice of the other one if you wish. Okay, I spoke very quickly. You might have to listen to that again to get anything out of it.